Hi everyone, I'm Inbar and Yaacov, and today I'll talk about explicit binary tree codes with sub-logarithmic size alphabet. This talk is based on joint work with Cohen and Yankovitz. Tree codes were first introduced by Leonard Schulman in the early 90s as a key ingredient for interactive skills. A tree code is an infinite binary tree together with the coloring of its edges, where the colors are taken from some color set sigma or alphabet. We require that the tree has the following notion of distance. For every two vertices of the same depth, we consider the path from their least common ancestor to them and take the fraction of colors in which these paths differ. For example, considering the highlighted pair of vertices U and V, their least common ancestor is W, and the bolded edges are the examined paths. We can see that the colors along these paths differ in 2 out of 3 edges. Hence, the distance between U and V is 2/3. We define the distance of the entire tree to be the infimum of the distance over all such pairs of vertices. When we talk about tree codes, we usually consider the following properties. The first is the number of colors we use for coloring its edges or its alphabet size. The second is its distance. If a tree code has both constant number of colors and constant distance, we say that it's asymptotically good. The third parameter is whether or not it is explicit, where by explicit we mean that we can compute the color of each edge in polynomial time in its depth. So now that we know what tree codes are, we naturally ask what they are good for. First, consider the case in which Alice wishes to send Bob a message over an imperfect channel. We all know that Alice can apply block error correcting code to a message to get an encoding C of X, which is linearly longer than its original message. Then she can send it to Bob so that Bob can recover the corrected encoding, even if a constant fraction of errors has occurred. Here we consider a different setting. What if, instead of sending a single message, the two parties want to have a long conversation? In this case, each message depends on the prefix of the conversation carried so far, and the fraction of errors that may occur is a constant in the conversation's length. Applying a standard error correcting code won't provide a satisfactory solution, since to interrupt the conversation, all the adversary needs to do is corrupt a single message. This costs a vanishing fraction of errors in the length of the interaction. It is not at all clear that a good solution even exists, meaning that one can pay a constant factor in the length of the conversation to enable Alice and Bob to interact despite a high frequency of errors. That's the point where tree codes join the game. They play an analog role to standard error correcting codes for the case of interactive communication. In his seminal work from the early 90s, Leonard Schulman proved that the existence of tree codes implies resilient interactive communication. Further, he proved that asymptotically good tree codes exist. That is, for every delta between 0 and 1, there exists a binary tree code with a constant alphabet and distance delta. In addition, Cohen and Samocha proved that 4 colors are sufficient and necessary for constructing an asymptotically good tree code. Unfortunately, all the above were proved by the probabilistic method, hence don't provide an explicit construction. This day, constructing an explicit asymptotically good tree code remains an elusive open problem. Here is a brief history of what is known today about explicit and deterministic tree codes. The Holy Grail is to construct an explicit and asymptotically good tree code, but such a construction is not yet known. The trivial solution is to allow 2 to the n number of colors at depth n. This enables one to color each vertex of the same layer with a unique color, hence achieving a perfect distance of 1. In 1994, Evans, Klugerman, and Schulman presented a polynomial alphabet construction for every constant distance. In 2016, Gales et al. Focused on constructing a tree code with a constant number of colors and a vanishing distance. That is, in their tree code, every 2 vertices of depth n have a distance of at least omega of 1 over log n. A bit later, in 2018, Cohen, Hapler, and Schulman managed to construct tree codes that have polylogarithmic number of colors for every constant distance. In another result from 2020 by Narayanan and Weidner, the authors achieved the same parameters as Cohen, Hapler, and Schulman, together with a randomized encoding algorithm for a large enough radius. One may hope that giving a conditional asymptotically good tree code that its distance guarantee relies on a not yet proven mathematical conjecture may be an easier task. It seems that even that is quite difficult. This day, there are 2 candidates. The first is a beautiful construction by Moore and Schulman from 2014, which provide a conditional tree code that its distance guarantee relies on a conjecture about exponential sums. The second candidate results from joint work with Gil Cohen and Anand Kumar Narayanan from 2021, which presents a construction whose distance guarantee relies on a conjecture we put forth regarding the zeros of certain polynomials, often over finite fields. And there are many other works in this area. Prior to our work, the results that achieved the best parameters were those that highlighted in green. The one by Gales et al. That reached the best distance with a constant number of colors, and the work by Cohen, Hapler, and Schulman, who from now on are referred to as CHS, which achieves the best alphabet size for every constant distance. In this work, we improve upon both of these results. For every small enough delta, we present an explicit tree code with sub-logarithmic number of colors and distance delta. This result improves the one by CHS, as it requires a polylogarithmic number of colors for any constant distance. As an immediate corollary, we get an explicit construction for tree codes with a constant number of colors and distance of omega of log L to the power of -2. This to be compared with the construction by Gales et al. That has a constant number of colors and distance of omega of 1 over log L. Before presenting our work, I need to set an equivalent definition for tree codes, which is less intuitive but much easier to work with. But even though we move further away from the intuitive combinatorial definition, we borrow the terminology from the presentation of tree codes as trees with some distance property. First, we define the split of 2 distinct strings to be the minimal index in which they differ. We say that the function f is online if for every input x and every index I, the I symbol of f, when evaluated over x, is determined by the prefix of x after the I symbol, namely xo to xi. And now for the definition of tree codes. An online function is said to be a tree code with distance delta if for every distinct input inputs with split S, no matter how far we look from their split, this is what L stands for, the relative Hamming distance between the two evaluations when we consider the substring starting from S to S plus L is at least delta. Natural relaxation of the definition for tree codes is considering a tree code of finite depth. It is clear that infinite tree code implies finite tree codes of any depth, since one can truncate the infinite tree at any desired depth and get a finite tree code with the same properties she began with. A natural question is whether the converse also holds. Namely, does an infinite family of finite tree codes of every finite depth that share the same number of colors and distance implies an infinite tree code with comparable parameters? Apparently, the answer is yes. As part of our work, we proved that an infinite family of finite tree codes with distance delta and sigma colors implies an infinite tree code with distance delta over 2 and sigma cubed colors. In fact, it's sufficient to have a tree code of depth 2 to the n for every positive integer n. Therefore, we can focus on constructing an infinite family of finite tree codes instead of a single infinite one. We get the intuition for our construction from this of CHS. As part of their work, the authors considered non-binary finite tree codes, and for every positive integers m and l, they constructed the tree code of depth L and arity of 2 to the m that has 2 to the 2m plus L colors. All the trees have distance of 1/2. Now that they have a finite infinite family of tree codes, they need to reduce their arity to binary. Know that by naively setting m to 1, we would indeed get a binary tree code, but its number of colors is exponentially large. However, m and l have an additive relation. The authors use this property to cleverly reduce the arity to binary while getting a polylogarithmic number of colors. But I won't get into further details of the reduction. Our strategy is to exploit the decoupling of m and l differently. We present a transformation that, given a tree code of certain properties, transforms it into a tree code that its number of colors has a better dependency on itself. This way, we can repeatedly apply this transformation until we can no longer reduce this dependency. To achieve this goal, given a distance delta tree code of the presented form, we'll break its exponent of number of colors, k, into 3 components. Its non-trivial dependency on m is captured by alpha, and its dependence on the depth L is captured by beta and gamma. We call such a tree code by alpha, beta, gamma, delta tree code. Hence, we devise an efficient transformation that reduces the dependency on gamma while not deteriorating alpha and beta too much, and further, not harming the distance at all. This is since even the smallest constant deterioration will cause a vanishing distance when applying the transformation iteratively for a non-constant number of times. So here is one of our results. There exists an efficient transformation that, given an alpha, beta, gamma, delta tree code, it transforms it to an alpha plus square root of delta, beta plus square root of delta, gamma over 2 delta tree code. We can see that the resulted tree code has a better dependency on gamma and the same distance as the original tree code has, as we wished. A small note I want to mention. Our transformation requires that m is at least logarithmic in the depth of the tree, which doesn't allow us to feed it with a binary tree code, hence also not achieving one. However, we can take m to be log n, and use a well-known and efficient transfer reduction to binarity that has almost no cost in parameters and works for the regime of m equals of log L. In our notation, the CHS construction mentioned above is a 1-1-1-1/2 tree code. By a simple tweak, we deduce a variation that is a delta-delta-1 tree code for every delta in the range of 0-110. Then we set this variation of CHS construction as an input for our transformation. This yields a tree code with the parameters presented below. Now we take the resulting tree code and feed it to the transformation to further improve its parameters. Keep doing this process iteratively for r times yields a twice r times square root of delta to the power of minus r delta tree code. And by setting r to be log L, we eliminate the additive dependence of the number of colors on the depth and obtain a distance delta tree code with an arity of 2 to the m and 2 to the o of square root of delta log L times m number of colors. As a last step, we get our desired binary tree code by applying the well-known arity reduction mentioned earlier. Now that we get the big picture, we are ready to understand the transformation. Recall that we want to transform an alpha, beta, gamma, delta tree code of depth L to one with parameters as appearing here, that has distance delta and depth L squared. We will explain it by describing how the output tree code acts on an input. Given a message of length L squared, we write it in an L by L matrix as appears in the illustration. Then we apply the tree code we get as input over each row. Now that this operation is well defined. Then we take a suitable variation of the CHS construction with distance square root of delta, which we refer to as TC-mat, and apply it to the entire matrix. In addition, we reinterpret each output symbol of TC-mat as a string of length L and apply it to its standard error correcting code with distance of square root of delta. Now for the distance analysis. The highlighted green cells are the parts from the encodings starting from the split to some point farther away on which the tree code is being tested. Recall that in order to have distance delta, the tree code has to have distance delta for all possible such tests. So the first case is when the entire test is contained in a single row. In this case, the input tree code provides us a distance of delta. The second case is where the test contains a complete matrix row. In this scenario, the variation of CHS construction together with the standard error correcting code we applied guarantee distance delta. But what if we have neither? A partial solution is obtained by using a reverse polynomial. For each row, we define a polynomial that reads its coefficients from the previous row in a reverse order, from right to left. Then we evaluate the polynomial over distinct field elements and write the evaluations in the respective row. Note that since the coefficients are taken from the previous row, evaluating the polynomial can be done online. However, this solution is not complete. What if all the polynomial roots happen to be printed at the beginning of the row, and the test doesn't include enough cells? In this case, we must rely on the given tree code, which is applied to the rows, but then the distance will deteriorate. Our solution is equipping it with another notion of distance, which kicks in only when it completes reading its inputs. More formally, we say that a tree code has a suffix distance of big delta if for every distance distinct messages, the relative Hamming distance between the two evaluations, when we consider the substring starting from the split to the end of the encodings, is at least large delta. Hence, before applying it to the rows, we equip the input tree code with a suffix distance while paying a small factor in alpha. Combining the above solutions, when set with appropriate parameters, gives us the desired distance of delta. Now we turn to analyze the number of colors. Here also, there are some problems we must address. For example, what happens if we output the encodings of both of the tree codes we use? Recall that each tree code outputs at least one symbol per every symbol read. Hence, if we naively output both, we get that alpha is greater than 1. This yields a binary tree code with at least omega of log L colors, which gives the same parameters as CHS. This is also the reason we couldn't afford to use the original 1-1-1-1/2 CHS construction, but had to relapse it to a delta-delta-1 delta tree code. Another remark is that restricting alpha to be smaller than 1 also prevented us from using a standard shifting solution for dealing with the case of a test that includes 2 non-full rows. To solve this problem, we use systematic encodings. Informally, we say that an encoding is systematic if its input appears in the output. Since the CHS construction is systematic and both of the tree codes are applied to the input message, we can output the systematic part only once and output only the redundant parts of the tree codes and the error correcting code we use, while making sure that all of the above are not too parsy. Another problem is caused by writing an evaluation of our reverse polynomials for every input symbols we read. This results in the same problem as in the previous case. Our solution is to output a symbol only once per C symbols read and spread it over C output symbols. By taking C to be the parameter that gets the best results in terms of distance and number of colors, we get the desired results. Concluding it all, with these solutions in hand, the number of colors required for the resulted tree code is presented in the slide. By applying the transformation iteratively, where the initial input is the delta-delta-1 delta CHS construction, and then reducing the arity to binary, we get an explicit binary tree code with a sub-logarithmic number of colors. Thank you very much for watching.